Hello learners, I hope you're keeping well and I hope the geography is going well. We're getting nearer and nearer to the end of the year. Today I'm actually going to deal with two sections. I think many of you actually complain about the difficulties of the sections, and that's GIS and map projections. Now, what I'm going to do is I am going to look at the content that needs to be covered for examination purposes. And I'm also going to look at possible exam type questions. Let's go a little further. Right, just a little points to you guys is that many learners feel or have problems looking at the section, we don't have computers, how are we going to do GIS, etc. Now, obviously in exams, you're actually not going to have a computer in front of you. So you will be not using computers during the examination. But most of your questions will be based on the maps and photos and even diagrams. So it's not that intense GIS that people go in and spend a lot of money spending and doing GIS courses and advanced courses in it. It's more the basics of GIS. All right, we will need to know that the topographic map and the orthophoto map you receive during the exams are similar to GIS in that different types of relevant information are put together to make them. So we have different layers, etc. So they're similar to GIS. Therefore, we can test you on the topographic and orthophoto map for GIS. All right, if we look at it again, topographic maps are a representation of reality and shows us how things relate to each other in space. So it's spatial data. Okay, and nowadays we're getting a lot of our information to be put onto maps, etc. from GIS. Okay, including the orthophoto maps, which are accurate aerial photographs. And it contains information such as contour lines, spot heights, names of places, etc. And nowadays, we can get all this information from above via satellites, etc. And we can get this picture. So there's a strong relationship between your topographic maps, your orthophoto maps, and GIS. But let's look at a simplified version of what you need to know. Okay? Now, I think even before this, it's basically four simple things. Okay, I'm going to extend the page here. The first thing you'll need to do is know a brief description of GIS. Okay, and the second thing you would need to know is certain concepts. I will cover these concepts here. Concepts related to GIS. Thirdly, the components of GIS, and lastly, how could we use GIS in our daily lives? Okay, that's basically it. If we could cover this, also in fact with the concepts, if we could apply the concepts, we would be fine if we know these four things here. So this is basically what we need to look at. So let's start looking at the concept of GIS. All right? Obviously, you know that GIS stands for Geographic Information Systems. All right? Let's split this word up first. Geographic, referring to a place on Earth. It's spatial, because everything has different spaces. It's spaced out, so it's spatial. all right? Where something is on Earth, location, okay? And then the second word, information. Of course, that refers to data or facts put together. That could refer to layering, but I will deal with these concepts in more detail as we go through our session. To make sense, okay, if we're looking at a specific thing, for instance, we want to find out the best place to buy or to put up a shop rather, then we would look at where the need is and we'll collect certain types of information. Or we want to build a house and we want to look at where's the least crime. We will get information about the different areas and find out which is the safest place. So it's data, putting it together, making sense. Example, the number of people using a road. Do we need to upgrade the road? Okay, you'll find those little black cords on the road, which then count number of people in order to determine whether we need to widen the road. But this is all data. Data is also used in GIS and can be following in terms of maps, remote sensing. I know you may be not, some of you may not be familiar with this, but like things like remote sensing, I will come to it at a later stage. Spatial resolution, spectral resolution. And the last word on GIS is system. System referring to interrelated information using data to mean something. We may have all this data, all right, all this information available, but we look at a query. What do we want to find? So we have all these crime statistics, or we have all these information about where we want to shop, or where we want to put our shop, but we want to know what is our aim. Our aim to determine the safest place to live. So we take all the information on crime that's related to the areas we look at, and then we determine which is our safest place. All right? So in other words, the definition then is that GIS is an organized collection of computer hardware, that's your computer itself, software, that's the programs, geographic data, that's the data that you will be using, designed to capture, store, update, manipulate, and analyze and display geography reference data. A lot of big words here. Okay? So let's simplify the definition itself. Okay, I'm going to go down here and extend this page. I could then say GIS is a collection, I'm putting it in my own words, collection of digital data which tells you more about a place or location. All right? That could be a simpler version of the definition. All right? So we're going to look at all these things. This actually in a nutshell summarizes it. So we're looking at all this digital data that's coming through via satellite. Okay? It covers landscape, it covers vegetation, it covers settlements. It gives us a picture of what is going down on Earth. And the beautiful part is we don't have to visit those areas anymore. For instance, I want to find out a little bit more about what's happening within the Amazon. If I set my coordinates, I could focus down there, or if I want information, I could get it via satellite and via GIS programs and find out exactly what is going on in those areas. If I need to buy a farm in Zambia, I may not have to go there at first. I can get all the different information about the area itself. You understand the fertility of the land and the price and all those factors, and then make a decision and then go there. So it makes life easier. It's this collection of data. So it's organizing, collecting. Obviously, we'd need a computer. We need the program. As we said, the software. We need all these aspects. This definition then we could look at in terms of the components of GIS. All right. Now, GIS basically has 5 components. 5 components. The hardware, as it was found in that comprehensive definition, the software, the data, people and organizations, and processes. Okay? GIS has the same components as other information systems, as I will show you now. It allows us to collect, store, process data to produce maps and answer spatial queries, to answer certain investigation. And we even produce our maps when we collect all the different data such as roads, railway lines, vegetation cover, gradient, landscape. All these things we can get, and we actually put them onto one, we actually layer them, put them all together, and we have a map. Okay, let's look at the 5 components. Now we can actually compare the 5 components of GIS to a car. I would love this to be my car, but unfortunately it's not. It's one of those sports cars which I cannot afford. Okay, but let's look at it. Right, let's take the first one, the hardware. This is an easier way of understanding it. All right, the hardware itself is like the body of the car. The body of the car. It won't look very good if you don't have a body of a car. All right, and then you're going to sit in it. There'll be huge problems. So same way with this program, the computer hardware, the central processing unit, all right, the monitor, the keyboard, the scanners is like the body of the car. You need all these things. Okay? Then if we look at it, you need the petrol in the car. Obviously, if you've got the body, you need the petrol. And if you don't have petrol, you can't move anywhere. So the fuel would be the next thing. The fuel could represent the data. Okay? So you would need data in order to determine, if you got a query, I want to find out which is the shortest road to school. I need data in order to determine that. So it's the petrol which gets the car to move. And maybe I should have explained this before. The software, the program itself, could be the engine. Because without an engine, the car can't move. So that is your software. You can have millions of pieces of data, but if you don't have the software in terms of processing that data, you can't do anything with it. So the engine itself becomes the software where it's being processed. Okay? So we looked at the body, which is the body of the car, which is the hardware, and we looked at the engine, which is the software, the programs. Once we got that set, we're looking at the fuel of the car, which makes it actually go, and that would represent your data, your information. And obviously, I know the future, maybe we don't need drivers or something of that sort, but at this stage, we do need a driver to drive that car. Otherwise, it's not going to move. So in this way, people or organizations are needed. And that's like the driver of the car. So if you relate it to the car itself, you will see that the 5 components which I've highlighted here, the hardware, the software, data, people and process, organizations and processes, are extremely important. We need all these 5 things in order to operate GIS successfully. Okay? Let's then look at some of the concepts, and must remember that we need to apply these concepts also. Okay? And one of the big concepts is remote sensing. Now, I've got a little picture here. All right? There's your satellite, and there it's actually taking images or digital images or whatever images of the Earth. Okay, that's remote sensing, picking it up from a distance. So getting data about the Earth's surface from a distance. Example, satellite images, okay, used for various things. In fact, your meteorologists also now depend on satellite images in terms of drawing up your satellite photographs, etc. The beauty part is we can actually zoom in. If you've got those cell phones, those advanced cell phones, not like mine, the ones that you guys can afford, those expensive ones, you can go onto Google Maps and see how you can actually zoom in. You may just get an outline like this, and then if you zoom in, you understand you can actually see the places or even the houses or the swimming pools. It's fantastic, but it's taken from a distance, okay? This is another image taken from a distance. Okay, you'll see the outline to a certain extent, you can see the landscape, but you can be zooming in to make it clearer. So remote sensing is when it's taken from a distance. Let's look at resolution. That's the next thing. All right, this is the detail and clarity of images, all right, in satellite and aerial photographs. You have to look at a satellite photograph and you look at an aerial photograph. I did not put an aerial photograph here. I tried to create my own little thing with maps. Okay, it may not be the genuine product, but it actually shows something here in terms of clarity. If you look at this one, it's far clearer than this one. So clarity. So here the clarity is good and here the clarity is not. Okay, so that's resolution. And also detail. The amount of detail that you can actually see regarding the area, maybe the landscape, maybe the rivers flowing through the area, you can see it clearly. That would be resolution. Okay? I think you will use that a bit also when you looking at buying your TVs. We'll come across another thing also with pixels that make things clearer. So that resolution. The next one is spatial resolution. Spatial resolution is the detail with which the map shows the location and shape of geographical features. All right? Location and shape. So what would fall under this one? Location and shape. Location could be your coordinates. All right? Some of you still use the old term grid reference. Coordinates. Okay, and if I'm looking at the shape of an area, all right, that could be a dam, okay, and we could see the nice outline of the dam. So your coordinates and the shape of features. Coordinates could be 25 degrees, 16.2 minutes south, etc. Okay, so that would relate to that. Then we look at another question with regards to spectral resolution. Refers to different kinds of information that can be collected. All right, we'll get various types of information. I will be coming to that at a later stage in terms of looking at the different types of information that can be collected. You can get information regarding the landscape in terms of the gradient. You can get information regarding the vegetation. So there's various types. Spectral resolution. Database is actually a storage system linked with the tables, etc., that you're using. So I will store my information under the memory. I will have different types of information. If I'm looking at, I want to get something about, let's say, the shortest route to school, then I will go into the database which stores the information, distance from school. I may look at the easiest route to the school besides just looking at the shortest route. Gradient. Maybe this one route may be shorter than the other, but the gradient is very steep. Okay? And because the gradient is steep, it would be a problem for me to walk to school. It may take me longer. So I could consider various things, and I would have to go into a database to find this information. All right? Data itself is facts about the reality that have been observed and measured. When data is stringed together, it forms information. Okay? It may be information at first in terms of data, but it makes more sense when it's stringed together. Again, let's use the example about the easiest way to get to school. I'll look at the distance from the different routes. I'll look at the gradient from the different routes. All right, I'll look at maybe traffic on the different routes. I'll consider all this, you understand? And it forms my information which I'm investigating. Okay, let's look at a different type of data that we could get. Okay, let's look at paper maps. That's one form of data that I could use. Okay, satellite images. Okay, taken from above. Okay, the resolution is not very good here. It's not so clear, but this is an image taken of an urban area from above. You can see the buildings and the road networks, etc. Okay, digital maps of an area taken by a satellite, etc. Here we can see clearly the different vegetation areas, the green covering the area. Then there's tabular data in the forms of tables. All right. Then there's the global positioning systems, that's your GPS. And of course, you could use your cell phone in this area. I know this is quite an old one, all right? And you can use your GPS monitors, which your dad now makes life easier for you guys. When you're going on a holiday or something of that sort, all you need to do is press where you want to go, the street name and the province, etc. And there it sets itself for you. Okay, and you can travel. So this is the global positioning system itself. Let's look at the next related concepts. Now, I'm going to talk about two other concepts, and one is spatial. Spatial data, and that would actually refer to the location and shape of the feature. Okay, the location and shape. We had spatial resolution early on, which spoke about the clarity of the coordinates and the shape. Yes, spatial data focuses on the location. So we're looking at the coordinates. All right? Earlier on, maybe I shouldn't have written the word under coordinates under spatial resolution, but it does cover that. But there it's a clarity. Here it's the data, the coordinates itself, like your degrees south and east, etc., and the actual shape of the area. All right? So that's spatial data. Then we look at attribute data. They both are related. Attribute data. And this is when we locate the shape and the location, or more important, the location, then we look at information about the location. So attribute data is information all right, or information about the location or the point that you actually located, location or area. All right, so what would be some of the attribute data? All right, I located the place, now I want to know more. Obviously in real life also, if I want to find out more about an area, I'll locate it first. That will become my spatial data. And then I want to find out exactly what I need to know. Okay, maybe I could look at things like the temperature of the area. Maybe you want to go on holiday, and I'll look at the temperature of the area. Okay, I may want to look at the landscape of the area, the landscape. Sorry, my little pen stopped working. The landscape. Okay, what is available in the area? Okay, maybe a dam, a river. Okay, maybe lovely mountains are available there. This is all further information about the area. Okay, rainfall, maybe I'm going to go there and suddenly if I don't investigate it properly, this is the rainfall season and I may not have a good holiday. So this is basically your attribute data itself. Okay, let's look at further concepts related to GIS that you will be tested on. The next two concepts also, we can look at them together. Vector data, representations of an area using points, lines, and polygons. Now what's those points, lines, and polygons? Points are little dots, okay, there we are here, and they could be a spotlight, a school, a church. Those are little points, okay, that's found on a map. Lines, obviously, as you can see down here, your lines, which could refer to your roads, your railway lines, your rivers, your farm boundary, okay, your windbreaks, which could be along in a line, okay, and polygons are closed features like this one, which could refer to your dams and things like that, okay. This is your vector data. Where it's used a lot on, it's used on maps and things like that, where if you look at your topographic map, you will find that there are lines, there are dots, there are symbols for dams, okay, that's your vector data. All right, you can see it down here, okay. There is, this could be a polygon, it's cultivated land. There's a road here which shows you a line, okay. I can see a little dot there, okay, that is your points. So all this, the dam down here is your polygon, it's closed feature. So that is your vector data. Now raster data actually deals, it's a representation of an area using rectangular grid cells, okay, referred to as pixels or picture elements. Interesting one, we use this quite often. I know many young people sometimes say, but my camera has got 14 megapixel in it, you understand? And you ask them, what is it? Okay, it's all little blocks. And the higher the pixel, the more blocks there are. Now what actually happens is, if you have more pixel, you have more blocks. So it's similar to, like if I give you a room, you understand? And I divide it into 4. And I make 4 people clean each spot. Okay, they may do a good job, all right? I take the same room and I put 100 people and I divide it into 100 blocks, the same size room, and people with the same effort. And I make them clean those little blocks and I give them the same amount of time. You'll find they clean the blocks better. So I always use this example, although not totally related. So each block will focus. If the blocks are smaller, each one will put in the same effort. And what will actually happen, the clarity of the picture is better when there's more pixel. All right, and now some people buy a big TV and it costs 6,000 Rand. And somebody buys a TV this size, especially those HD TVs, and it costs 8,000 Rand. And you must say, but a big TV, small TV, why is a small TV more expensive? Maybe it's got more pixel, and therefore it's more clearer to use. Now, this is your raster data, okay? It's a picture, okay? It's photographs, it's whatever. Your autophoto is raster data, all right? And of course, the more pixels we have, the clearer the picture, okay? Your satellite image down here is raster data. Okay, let's look at the next concept, data manipulation. When data is processed and converted into useful information. Example, correcting distortions and sharpening images. Now earlier on I showed you those 2 pictures. You understand? Maybe I want to go back to that very quickly. Okay, I know I covered quite a few concepts. right, where I showed you those two maps, right, down here. Okay, if I had this as an image, it's not clear. So I want to sharpen the image. Okay, in that way it makes my picture clearer. So data manipulation is converting it to more clearer pictures, also more useful information. Okay, I may go in and get, I'm sorry I'm using the word crime all the time, but it's an example, all right? I get crime for the whole country, for each area, but I want to look at crime in Johannesburg. So what do? I manipulate data, I get the necessary data that I need to use so it becomes more useful. I may not need information about Durban, etc. Okay? So better clarity, as I did put it down here, clear and not so clear. Okay? The next point is buffering. I know many learners don't like this concept, but it's actually very simple. It's a zone drawn around a mapped feature measured in units of distance or time. So what do we mean by a zone? All right, we can get different types of zones first. Okay, there's a river here. Okay, and there's a zone created around it. That's buffering. All right, that's line buffering. Then there's a point here, which could be a settlement or anything of that sort, and then there's a buffer zone around that. And then we got a polygon feature and a buffer zone around that. So that's buffer zones. Let's just get back to what is the purpose of this. Okay? Now, there's a river here. And this river may be in danger of flooding. All right? Now, I need to limit development around this area. I need to say where we can develop and where we can't, because sometimes if you develop too close to the river, our development, our urban development, or we're building a resort or whatever, could be flooded and it could endanger people and damage infrastructure. So I need to know up to which point would it be safe for me actually to allow development to occur. So I'll assess the river and the amount of water in it and the chances of heavy rainfall, and if it floods, up to which point. And maybe in this case, I realize that the river is in danger of flooding up to there. So I want to create safer, so what do? I make it a bit bigger, and I say, okay, you cannot develop any infrastructure or buildings or whatever in this area. You can only develop after this zone. Now this is known as buffering. We use it very regularly. You understand? In terms of determining things like that. Okay, look at this one. This may be a city. Okay? And we say, hey, we want to determine, because if these cities carry on growing, this city could meet this city. So we say, sorry, your development of this city is only up to that point. After this, it's conservation area. You can't develop there. So we have a balance between the natural environment and the man-made environment. Again, this is buffering. Quite an interesting concept. Okay? Spatial analysis. Okay, and a statistical analysis rather, interpreting various forms of statistics in relation to the query. I know today I'm a bit stuck on the crime rates. I was just recently looking at some articles over the internet, and therefore I found this. I want to find out which city. Okay, I will maybe do a comparative study and find out which city has the highest rate of crime. And I don't know, I cannot verify whether this is correct. It's one of the things that I've picked up from the internet. So it stands, maybe it's just an opinion, I don't know, but I'm just using it as a graph. And from here, I get statistics to sort out my query. And I look at Johannesburg being the highest compared to the others. But I looked at the statistics and then made my decision. So statistic analysis is analyzing different figures. Even here, okay, I was looking at the different crime categories, and I want to look at the different types of crime that happens, and I'm comparing a year of 1994 to 1998. But I need statistics, and I need to analyze them to determine which year was worse. Okay? Next one, database is the next concept. It's a collection of data organized for use in computers. Okay? This image came a bit blurred, all right? But you can see then we can also say that the resolution is not very clear here, all right? But I could use various data. Let's look at this one. I'm constructing a map. I'm looking at the road networks. I'm looking at the railway networks, all right? I'm looking at the water supply. I'm looking at the vegetation, okay, because I want to construct a topographic map. So I'll have to get all this data and then organize it on my computers. Okay? Thematic layering, it shows the different types of information, that's projected onto one another and placed on top of one another. All right, that's creating your map. I'm going to go back to this one. There's the different types of information. And then I place them on one another and I create the map, which will have the road networks, it'll have the roadway networks, railway networks rather, it'll have the rivers, all that information, it'll have topography, all put onto one map itself. Okay, that's thematic layering or data layering itself. Okay? And data integration also, putting together various sources of information. Very similar. You understand? Okay? Putting together various sources of information. It could again be referring to different things such as transport and things like that. Okay? And lastly, the last point. So we looked at various things. The concepts, the concept of GIS, the components, and then we looked at the concepts related to GIS. How do we use GIS in our lives? Okay? I gave you some examples here. Agriculture, we look at rainfall patterns. We can actually monitor that, predicting the climate, the soil type, the stability of crops. We can look at it over some time. Then we look at crime prevention. We can look at crime statistics in spatial patterns. Where it's higher, do we have a need for more police stations in that area? Or are they enough? Okay. Traffic congestion, controlling traffic lights. Okay, we can monitor traffic that is happening, and maybe we need to make, if we got two roads, both leading in different directions, and maybe this way there's less traffic, and on this side there's more, where it's passing the robot. So maybe we could make the time longer for the traffic lights to be on green so that cars can pass through here, and maybe shorter here. Or maybe sometimes we need to look at putting in robots in areas or putting in four-way stops. So controlling it. Financial, banks monitoring customer patterns of behavior. All right? What do they like? It doesn't necessarily have to be just banks. It could be any businesses. They monitor the behavior of people, the movement from where they are coming to buy at this place, or do their business, or what do they prefer to do in terms of businesses. Okay? Mining, exploring the mineral deposits. Okay? Again, we can use satellite technology to explore these things, where the distribution of minerals, etc. is. Personal use, finding the shortest route to school, buying a house, and which is the safest place to buy a house. So you can use it in daily life also. There are so many uses. It can be used for elections, to set up polling stations. Where do we need more of? Where's the people distributed? Okay, we can look at issues such as climate change with global warming. All right, climate change, you can see satellite photographs of how the ice caps are melting, which is giving you evidence from before to now that there's more ice caps melting. So there's so much that we could look at in terms of GIS. It's the way to go in the future. You understand, it makes our life easier. We have the information ready. We can get our information at our fingertips. So beside being an important section in geography, which you will be tested on, it's also an important aspect in terms of our changing times of technology and for use in our life. We'll take a short break, and you can quickly go and get that glass of water and get back for the next section. Welcome back, learners. We come to the last part of this session where we're going to look at map projections. Now, I know people try to avoid this. I know the fact that it hardly comes out. I know in the last few years, basically we asked you what type of projection is used on maps, on our South African maps, but nevertheless, it's a significant section. We never know what holds in this year's paper. Okay, so don't just assume. It also gives you a foundation for the appreciation of topographic maps, etc. So let's have a peep. So I've got some little pointers for you here. All right, I'm aware that maps can or map projections can deal with a lot of complex detail, and learners seem to find it very difficult and confusing, which is a fact. All right. But again, here, as in GIS, learners need to know the basics of map projections. What is map projection? The convenience of using maps, projection properties and distortions, and different projection classes and associated projections. Okay, in fact, when I'm giving you the questions also, many of them are not exam type questions because they haven't hardly been set. Okay? I know this section, as I said, is hardly ever tested, but it is the basis to understanding and appreciating the designing of maps. That is not easy to design maps. And these people that design maps are very intelligent people and really have brought out wonders for us. Okay? So let's look at the definition of map projections, which we need to know. It is an attempt to portray the surface of the earth or a portion of the earth on a flat surface. A very difficult thing, especially when we look at our earth. All right, our earth is not round, as some people believe. It's a sphere, all right, ellipsoid, or even known as geoid. Okay, that's our shape. It's bulging at the poles, at the equator rather, and it narrows at the poles. You can see that is why your lines of longitude go in there. And that is why when you do coordinates, you notice that with lines of latitude, it's always 37 millimeters. But with lines of longitude, it can change. 32, 33, 34 millimeters, the distance between two longitudes, because it narrows at the poles. Okay? And we look at the distance at the equator, it's definitely more, right? And at the poles, it's less. Why do map projections? Now, I've got my little globe here. It's a bit of an ancient one, and it's a cheaper model. This is what I can afford, okay? But imagine I have this globe, and we're going to use the globe to actually do map work in class. Number one, I'm going to point it out here. Globes are accurate but expensive. Okay, they cost a lot compared to maps which are on paper. They are small scale and relatively detailed. Little detail on it. So the scale to fit the whole world, you understand, of the map of the whole world on a globe this size, you really have to bring the scale down and make it really, really small. So obviously when it's small, if I had to look at places, I know the camera won't show it, but you can look at globes at home, all right? If I look at Johannesburg, it just gives me the name Johannesburg. There's nothing around it in terms of the attribute data. You understand? It gives me hardly anything. Also, it's bulky to transport and store. Imagine every day you come to school with your bag and your lunch and your globe. Huge problem, okay? To carry it and then to store it everywhere. Okay, it's a problem. Okay? And if we look on here, I've got a few more difficulties with using this. It's the view, the perspective view, the view from a single point. If I want to compare this part of the globe to this part, I have to keep turning the globe. You understand? It may give my body a bit of exercise. Okay, but if I want to compare this to that, I have to look here, and then I have to look there and look here. And it doesn't make my comparison very easy. All right? Or I can view it directly from overhead from all points. You understand? You can't. Okay, but a map I can view directly. I can see all the areas that I want to look at. I can get different maps of the world or a specific part of South Africa. So, to take this globe, sorry people, and to put it on a flat piece of paper. Okay, that is map projections. And now we know we need the map projections itself. I'm not going to go into over detail, but I'm going to cover the basic aspects. Now, obviously, with map projections, there's going to be problems. You understand? Distortions, etc. Distortions referring to that we won't get everything the same. Again, taking our globe, which narrows at the poles, and then trying to make straight lines of longitudes, etc., is difficult. So we're going to get distortions. Okay? So some distortions, such as conformality, okay? What is the shape? It may be different. You understand? Again, I'm sorry, I'm keep pulling my globe out. If I put this on a flat piece of paper at the moment, you may see this better shape, and this is not a very good shape. Okay, so conformality with the shape, I may get some things looking bigger and some things, the shape looking, some shapes looking different to what it is in reality. Distance, I may not get the correct distance. If I start from the center of the map and go out, I may get a distortion. It may give me a shorter distance there to what it is on this side. So features may not be accurate in terms of their distance. Direction, on the map it may show north-west, okay, or north-northwest, but it may be slightly off in terms of the bearing or the true bearing itself. So I could get that distortion. I could get the area. It may look bigger than actually what it is, okay? Scale, I could have another problem with scale, where features may look, in certain part of the map may have a different sort of scale compared to the outer. Maybe if I have a map here, and the center of the map may have the right scale, and the slight scale may be slightly incorrect on the outside, okay? All right, so we have these distortions. Now, what would we look at here? The projections try to minimize these distortions. Okay, they minimize it, try to make it as accurate as possible. Again, it will determine whether what is the map trying to show. Is the map trying to show me more about, I'm using my map to show me about direction? Okay, so if I'm using direction, then I would try to make direction as accurate as possible. I want to calculate the bearings. I want to use the map to get from one point to the other. I make direction as accurate as possible, but maybe at the expense of the other properties. These are the other properties here. I may then don't worry so much about area. So area will be less focused on, and it may be more inaccurate, but direction will be more accurate. Okay, I could do it for any feature. I want to look at area. I could make that very accurate and the others not as accurate. Or I could take all the projections and try to make them as accurate as possible. You understand? And I will have my distortions down there. Okay, so I spoke about the projection properties and the distortions. Okay, let me get to the next one. The next slide is taking a little time. Then we look at different projections that we have. Very simply now at the moment, we looked at a definition, we looked at why we need to use projections and develop maps, and we looked at properties and distortions that arise from these properties. Then we have different classes of projections, of map projections, projection classes. The first one we have is cylindrical, okay? Under cylindrical we get a projection known as the Mercator transverse projection, okay? Mercator transverse projection. Here we use the cylinder method, and we're not going to go into detail. I'm not going to confuse you today. I'm keeping it to the minimum. Obviously, it's very interesting that you can go into more detail of how it goes. Here we use the cylinder method. You understand, around there we have the globe, and then we actually flatten it out onto a map, okay? And then we look at this one where we have the whole area, and we have our grid lines perpendicular. You don't see the bend in the lines of longitude. You see it as straight lines. Very similar to our maps, eh? All right, so that's your example, and you can see lines of latitude and longitude intersects at right angles. Obviously, I can go into more detail, but I'm not. I'm looking at exam purposes with regards to this. All right, this is actually good for the equatorial regions. Why is it good for the equatorial regions? Because it's more accurate here. Because as you look at the equatorial regions, you can see the lines are more or less perpendicular here because it's bulging. But as you go towards the polar regions, look what happens to the lines of longitude. It gets closer. So by making it perpendicular here, we're going to have some distortions. I'm using the word distortion there. Okay, but here there's less distortions, as you can see it down here. There's an idea of it down here. Okay, less distortions around this area, more distortions there. Okay, right. We're looking at the next one, which is a conic projection. And an example is a Lambert conformal conic projection. Most probably, if we had ever asked you, we'll ask you, give us an example. Again, I'm not going into detail. To just give you an idea, can you see the conic projections? All right, down there. All right, and you can see it creates a sort of tangent down here, okay, an angle. And because of the angle, when we spread it out, you'll notice that the lines of longitude radiate outwards, okay? The lines of longitude radiate outwards. There's another example of it down here, okay? So that is your conic projections. They radiate outwards. All right, and therefore it depicts shapes and areas well. It's good for east to west areas down here. It gives you better with regards to the shapes. Okay. Then we look at the projection, and we look at the azimuthal planar projection. Here we look at the tangent where it's taken from the top. Okay, it's like cut through there, and you can see the view. Can you see the circular view there? And you can see how it's taken from here, okay, from the top, okay? You can see the circle line there, and it's easier to watch or to view from the top, okay? Obviously, with this one, because it's taken from top view, example here is Lambert's equal area azimuthal, all right? The lines of latitude rather, are circular. Lines of longitude are radiating out. Can you see the latitude lines? Circular, and the lines of longitude radiating outwards. Okay? Obviously, because it's giving you a better view there, it's good for the polar regions. So when we looked at our other projections, you understand, then we found that with the conic projection, it actually made it better on this area, all right? And with the first one, when we looked at the cylindrical projection, it showed it better at the equatorial regions, all right? With this one, as we mentioned, from east to west, because it's focusing on that. And the last one here, which shows you around the poles where it's cut through there, okay, and that shows you better projections at the polar regions. And the last one is a miscellaneous projection. Miscellaneous projections actually include unprojected ones such as rectangular latitudes and longitudes, grids, other examples that do not fall into cylindrical, conic, or azimuthal projections. So this one covers a variety of projections. It actually includes those projections that we did before and includes things that are not included. A very general projection. Our Gauss conformal also may fall into cylindrical and fall into miscellaneous projections because it has various things. It tries to get the direction correct as possible. It tries to get the shapes of things. So it tries to minimize a lot of the distortions and focuses on a lot of things. This is your miscellaneous. Very simply, guys, these are your projections. Okay, and this basically, if you know this little bit of information that I gave you here, you would appreciate what is projections, the need for why we need to use it, the properties and the distortions, and the type of projection classes. Okay, and of course we'll specify which one is used in South Africa. If you do this information and leave this massive amount of information when you're doing it for study purposes, maybe you can go more detail in class, you should be safe. Okay, let's look at exam type questions. Now please, on many years, we didn't have any questions. We just asked you what topographic map, what sort of projection is used on our South African topographic maps. So many of these questions are not exam type questions. I've just created myself the examples of questions, so please note that. Let's look at this one here. Explain the term map projection, which could come out. Okay, and a solution easily. It's an attempt to portray the surface of the earth or a portion of the earth on a flat surface. This generally will come up for 2 marks. All right, state 4 types of projection properties: conformality, which we know is equivalence, equidistance, direction. Okay, any 4 properties, or you can speak about area, direction as the properties I gave you before. Okay, next one, explain the meaning of the map projection classes. What does it mean? It refers to different ways in which map projections are done. Remember, we did cone shape, we did cylindrical. Okay, we even created a tangent on the top with the azimuthal, and one has all types of properties involved, trying to minimize with the miscellaneous. Okay, so a definition. Next one, name 3 map projection classes and provide examples. We did cylindrical, which is Mercator. We did conic, which is Lambert conformal. We did azimuthal, which is Lambert's equal area azimuthal. Okay, simple questions. And of course, if I had to give this, if it's 3 marks, 3 there, you would actually, I don't think we would ever give so many. Most probably will give you 1 and give an example, because this one will add up to basically 12 marks. You understand? So most people probably would give you 1 and you give an example. Okay? And this is a common question that was asked on most cases. And the answer is on the topographic map. Refer to the figure below and answer the questions that follows. Now, if you look at the side of the topographic map, it says here which, let's put it down here, which projection is used in South African maps. Okay, that was a question. All right, the one, which projection is used in South African maps? And if you look carefully where the magnetic declination is indicated to you, in all our maps, when we set them, we try to keep them like that. Just above there, it says Gauss conformal projection. So we use this Gauss conformal projection, and that's your answer for that question, which projection is used in South African maps. Guys, very simple. Okay? If these little pieces of information are known, then you shouldn't have a problem with with map projections. Okay? As I say, it's not a question very often, but if it does, you should be safe with these types of questions being asked here. Because if you cover this content, it's not much. I hope you enjoyed the session, and I hope this fear of GIS and map projections is gone to a certain extent, because it is sections that you can score high marks in. All the best in your studies of geography, and remember, keep aiming for that A. It can be done. All the best, guys. Goodbye.